Welcome back to the deep dive. Today we are tackling, well, probably the most famous equation in history.
E equals mc squared.
Exactly. Just a few symbols, but it completely changed how we see reality.
It really did. It's this ultimate statement of symmetry in the universe. You have four simple symbols, a constant, a little exponent, and boom.
And suddenly two separate worlds, mass and energy, are just two sides of the same coin.
Precisely.
So our mission today is a deep dive into the life of the equation itself. We're not going to get bogged down in the math. Instead, this is more like its biography.
I like that, a biography.
Yeah, we're going to trace its family tree, the ancestors of each symbol, EMC, the equal sign, even the little squared.
And then follow its life from its unexpected birth in 1905.
Right, when Einstein was just a clerk at the Berne Patent Office. And then we'll get into its very dramatic adulthood.
War, medicine, cosmology, it's everywhere.
The real surprise here, though, is the conceptual leap it represents.
It's a huge one. Before 1905, physics had these two sacred, completely separate laws.
The conservation of mass and the conservation of energy.
Exactly. And this equation didn't just link them, it unified them. It told us that the total amount of mass plus energy is what's really conserved. And the human stories behind each of those parts are just incredible.
Okay, let's unpack that. Let's start with those ancestors. First up, E for energy.
And for that, you have to talk about Michael Faraday.
To really get Faraday, you have to understand what science was like before him.
You do. I mean, electricity and magnetism were seen as totally different forces. Not related at all.
One was the crackle from a battery. The other was the silent pull of a compass.
And no one saw a connection. Faraday's story is just amazing. He starts as a bookbinder, mostly self-taught.
Which turned out to be his secret weapon.
It was his huge advantage.
Yeah.
Because he didn't have a formal education. He wasn't, locked into the conventional wisdom that forces had to be straight line pushes or pulls.
So he could think outside the box.
Completely. And his big aha moment came after he saw a Danish lecturer show that an electric current could just slightly move a compass needle.
And he saw what no one else did.
He realized the force wasn't acting in a straight line. He visualized this space between them as being full of invisible whirling lines of force.
What we now call a field.
That's the concept, a field. This idea of an invisible conduit was foundational for the whole concept of energy as one connected system.
But his success didn't come easy. It had a pretty heavy personal cost.
Oh, it did. His own mentor, the famous Sir Humphrey Davy, accused him of stealing the idea.
That must have been devastating.
It was a huge public and professional blow. So damaging, in fact, that Faraday he retreated. He stayed away from frontline research for 8 years until Davy died.
A tragic story of professional jealousy.
Truly. But he laid the groundwork for energy conservation.
Okay, so that's E. Now for M, mass, and for that we turn to Antoine Lavoisier.
The great accountant of chemistry.
An accountant, I like that. He was meticulous.
Obsessed. Obsessed with balancing the books of nature. His whole thing was proving that mass is conserved in chemical reactions.
And he did that with his famous experiment, right? Weighing rusting metal.
Yes, in a closed glass container. He wanted to see if any matter was lost or gained.
Okay, so think about this. If you see metal rusting, it's crumbling, it's falling apart, you'd guess it weighs less at the end, right?
That's the intuition. But Lavoisier proved with incredible precision that it actually weighed more.
More? How?
Because it wasn't just decaying. The metal was actively combining with oxygen from the air inside the jar. He proved mass doesn't disappear, it just changes form.
So the total amount in the universe is constant.
Always constant. His precision in science was revolutionary, but his work in government, well...
That cost him his life.
It did. He'd helped build the hated tax wall around Paris, and years earlier he'd rejected an invention from an outsider.
An outsider named Jean-Paul Marat.
Who never forgave him.
Yeah.
So in the chaos of the revolution in 1794, Lavoisier was executed.
So you have Faraday establishing energy conservation and Lavoisier establishing mass conservation.
Two pillars, standing separately. Until Einstein.
All right, let's move to the symbols that bring it all together. First, the equal sign.
It's amazing how recent some of these things are. The equal sign was only introduced in 1543.
By an English textbook writer, Robert Record.
And his reasoning was just charming. He chose two parallel lines because no point two things can be more equal.
It's lovely, But the real importance is deeper. A good equation isn't just for, adding up numbers.
Right. It's not just saying 15 plus 20 equals 35.
It's a telescope for new ideas. It forces you to see that two completely different things, like mass and energy, can actually be equated.
That bridge is everything. Which brings us to C.
Celeritas, the speed of light.
Now, for the longest time, everyone just assumed light was instantaneous, infinitely fast.
Which would make it useless in an equation like this.
Absolutely. Then along comes Ole Roemer, a young Danish astronomer in Paris in the 1670s.
And he's watching Jupiter's moon, Io.
Right. And he notices its orbit weird. Sometimes Io appears early, sometimes it appears late. It's not consistent.
And he figured it wasn't Io that was the problem.
That was the genius of it. He deduced the issue was the time it took light to reach Earth. As Earth moved away from Jupiter, the light had a longer journey.
And he put his reputation on the line with a prediction.
A very specific one. His boss, Cassini, predicted Io would reappear at 5:27 p.m. on November 9th. Roemer said, no, the light needs more time to travel. It'll be 5:37 p.m.
In the actual time.
5:37 and 49 seconds. He was right. Light had a finite speed.
And it is an unbelievable speed. To put it in perspective for you, Ilya is about Mach 900,000.
It's hard to even get your head around that.
Think about it this way. If someone across a restaurant table speaks into their phone, the radio signals travel at the speed of light. The person on the other end of the call will hear the words before the sound has even trundled a few yards through the air to reach your own ear.
It's the ultimate cosmic speed limit. But in the equation, it's not just c.
It's c squared, which brings us to our last ancestor, the little 2.
And for this, we have to thank the Marquise du Châtelet.
In the early 1700s, there was this huge debate raging between Newton and Leibniz.
Right. Newton thought energy just kind of vanished in collisions, that God had to periodically step in and wind up his watch, so to speak.
And Leibniz believed it was conserved.
He did, but he couldn't quite nail down the math. That's where Emily du Châtelet came in. She was determined to find the experimental proof.
And she found it in an experiment dropping weights into clay.
Yes, from a Dutch researcher named Willems Gravesond. And the finding was stunning. A weight dropped from a certain height sank a certain depth.
Okay.
But a weight going twice as fast didn't sink twice as deep.
It sank 4 times as deep.
4 times. 2 squared. She realized that kinetic energy isn't proportional to velocity. It's proportional to velocity squared. Exactly. This was a critical piece of the puzzle. It proved Leibniz was right about conservation, and it put the mathematical concept of velocity squared right at the heart of energy physics. Einstein inherited that idea.
So all the pieces are on the board. We get to 1905, Einstein at the patent office.
And he has his core insight. The reason mass and energy have to be interchangeable is because of C, because nothing can go faster than the speed of light.
So if you keep pouring energy into an object to speed it up,
it gets closer and closer to that cosmic speed limit, but it can't break it. So the question is, where does all that extra energy go?
It'd have to go somewhere.
And the only place it can go is into converting into more mass. That's the leap. C squared is just the conversion factor, a huge one, which tells you that a tiny bit of mass is equivalent to a mind-boggling amount of energy.
We see this happen in real life, don't we, in particle accelerator?
All the time. You can accelerate a proton to 99.9997% the speed of light.
And what happens?
It doesn't actually swell up like a balloon. Its effective mass increases. It behaves as if it's 430 times heavier than it was at rest.
Because the energy you poured in became mass.
It did. And with that, the 2 separate laws of Lavoisier and Faraday were finally unified. The total of mass plus energy is what's conserved.
But it took a while before anyone figured out how to unlock that power.
Decades. The practical breakthrough really came from Lise Meitner in 1938.
She was in exile in Stockholm by then.
Right, fleeing the Nazis. And she was corresponding with her old colleague Otto Hahn in Berlin, who was getting these bizarre experimental results.
He was bombarding uranium and didn't understand what he was seeing.
And Meitner, using Niels Bohr's liquid drop model of the nucleus, had this flash of insight. She realized that an incoming neutron could make the big, heavy uranium nucleus wobble.
Like a drop of water.
Exactly. It wobbles until the natural electrical repulsion of all those protons inside just overcomes the strong nuclear glue holding it together.
And it splits. Fission.
Fission. And the math checked out perfectly with EMCO.
How so?
She calculated that the 2 smaller fragments, when you added up their mass, weighed slightly less than the original uranium nucleus.
So mass was missing.
About 1/5 the mass of a single proton. Gone. And that tiny, tiny missing bit of mass had converted into 200 MeV of explosive energy.
And what exactly is 200 MeV? Can you put that in context?
It's mega electron volts. For a single atom, it is a truly immense amount of energy. It's millions of electron volts, confirming this tiny loss of mass created a massive release of kinetic energy.
And this terrifying power immediately became a factor in the war.
Immediately. The German atomic project depended on getting heavy water from a facility in Norway at Vemork.
Why heavy water?
It was crucial for slowing down neutrons, which you
Yeah.
needed to do to get a sustained chain reaction going.
And that facility became a prime target.
The target of one of the most incredible sabotage missions of the war. In 1944, Norwegian commandos infiltrated the plant and managed to sink the ferry carrying the entire shipment of heavy water in Lake Tinzhou.
A huge blow to the German program.
It was pivotal.
Yeah.
It basically ensured their top scientists, like Heisenberg, could only get about half the reaction rate they needed.
So from warfare, let's shift to the cosmos. This is where the equation really reaches its full potential.
This is its adulthood, powering the stars. And the key figure here is Cecilia Payne in the 1920s.
She was at Harvard, and she challenged the accepted wisdom about what stars were made of.
Everyone thought they were mostly made of heavy elements, like iron similar to Earth.
But her work showed something completely different.
Through spectral analysis, looking at the starlight, she proved the sun was overwhelmingly made of hydrogen and helium.
Yeah.
Over 90%.
Which was not a popular finding at the time.
Not at all. Her superiors, especially Henry Norris Russell, basically forced her to add a line to her thesis saying her own result was almost certainly not real.
Just unbelievable, but she was vindicated.
Completely. And her discovery was the key. Hydrogen is the fuel. Her work proved that E&C ash is what powers the stars. The sun converts 4 million tons of its own mass into pure energy every single second.
And that process has sustained life on Earth for billions of years.
It's easy to think of this equation in these huge cosmic terms, bombs and stars, but it's also humming away in our daily life.
Okay, let's bring it down to Earth. GPS, we all use it. How does an equation about mass and energy help you find the nearest coffee shop?
It's all about relativity, which is the foundation of the equation. Those GPS satellites are moving incredibly fast, and they're in a weaker gravitational field than we are.
So time moves differently for them.
It does. It's called time dilation. And if we didn't use Einstein's equations to constantly correct for that tiny difference in the flow of time, your GPS location would drift by about 10 kilometers every day.
Wow, so it's essential.
It's the bedrock that makes the whole system work.
What about something older, like carbon dating?
Absolutely. Carbon-14 is radioactive. It's in all living things. And it decays over time by converting a tiny piece of its mass into energy.
A neutron becomes a proton.
Right. And by measuring how much has decayed, we can tell how old something is. Each one of those decays is a little ENCEAC event.
And you see it in medicine, too, with PE scanners.
And even smoke alarms. They use a tiny bit of a radioactive element that literally sucks mass out of existence to create a charged beam. If smoke breaks that beam, the alarm goes off.
It really is everywhere. Every click of a Geiger counter is a tiny echo of this equation.
A tiny confirmation that it's at work.
What a journey. From Faraday being ostracized and Lavoisier being executed, to the commandos in Norway and Cecilia Payne discovering the fire inside the stars. It's so much more than a formula.
It's a history of human curiosity, really, grappling with reality. And that grasp extends all the way to the end of time.
The equation even dictates the fate of the universe.
It does. Even something as extreme as a black hole, where gravity is so strong that pressure energy actually adds more mass, making it even denser.
Even they aren't permanent.
No. Over unimaginable timescales, trillions upon trillions of years, even black holes will eventually evaporate back into pure radiation.
Proving the final, absolute equivalence of mass and energy.
It's the ultimate symmetry. Energy created matter at the Big Bang, and in the far, far future, all that matter will return to a diffuse state of energy.
Leading to a great stillness.
And that leaves us with a final thought to mull over. If EMC holds true from the beginning of time to the very end, what does this fundamental equivalence of mass and energy mean for the biggest mysteries we face today?
I'm talking about dark matter and dark energy.
One seems to be just mass, the other just energy.
Exactly. Are they really two different things? Or are they, like mass and energy before Einstein, just two faces of a deeper unified reality that we just haven't figured out yet?